I think specific to your session, it is mostly around urban networks, like urban stormwater management. So we'll be focusing more on the stormwater networks towards the second half of the session. But first, maybe I'll give you a brief of TwoFlow, of what it is, what are the softwares it has, and what are some of the applications of the TwoFlow software. So I'll go through the presentation, and so you can stop me whenever you have any questions, or we'll have an detailed discussion towards the end of the session. So this is a overview of the presentation, what we'll be going through today. So as a brief, what do we do? So we develop and sell state-of-the-art 1D, 2D, and 3D numerical engines, and its supporting tools for simulating free surface water flow. As you can see, we are TwoFlow is being used by over 700 companies globally. Almost every country uses TwoFlow software, and it's basically originated in Australia in near Queensland University. So they are the people who has developed the software, and it has quite well spread across the globe. Australia and UK are the major countries who use TwoFlow, and in India, you can see these are the pink dots are the universities who use TwoFlow. So as of now, IIT Delhi and IIT Madras, and more recently, two professors from IIT Mumbai also has started using TwoFlow software. So it's getting quite a wide popularity, and I'll show you why it is getting popular. I won't go, this is a heritage of the software. I won't go in detail in this because we have short time. But in essence, what I would like to say is it started back in 1972 when TwoFlow has developed the S-tree. S-tree stands for the 1D model of the 1D component of the software. So initially S-tree was named as that so that because it was used for modeling the estuarine environments. You see the coastal estuarine environments. So to model those things, the S-tree was developed for the 1D mod component, but later the name has stuck in, and we still have the name as S-tree for the 1D part of the software. So, and as you can see here, from 2002 to 2006, the variety of third-party softwares providers who use TwoFlow engine for their graphic interface. So basically, SMS is quite popular. So they, even though they have a graphic interface, the engine which they use is TwoFlow software, Flood Modeler, XP Solutions. All these softwares use TwoFlow engine, and TUFLA has been very well benchmarked by various agencies. As you know, FEMA is the US agency, US government agency, and as well as TUFLO has been benchmarked for various studies by the EA. So one specific point to note here is that in 2017 was when there was a big transition in the TUFLO's history, when we had shifted from using a GPU of a computer to, I mean, the CPU of a computer to GPU of a computer. So now we are able to speed up the simulations as well as increase the accuracy of your models. So that has given to rise to a lot of huge benefits. I'll explain you those benefits in the next few slides. One important aspect here is also that TUFLO has been benchmarked for various tests against for the speed, accuracy, as well as model flexibility. So this is done by the ES Environmental Agency. So I would just like to show, let you know, like what are the benefits of having knowledge of TUFLO in Indian scenario. So there are various companies, various MNC companies. Basically, I was working part of Mott MacDonald previously. So this is a UK-based multinational company, and Waterco, Jacobs, Atkins, RV, ACOM, Worley Parsons. So these are all different companies situated in UK, Australia, even in India. They all the companies are there who use TUFLO, and they take a lot of people, a lot of water professionals into their team for modeling the flood models basically. So it is having like wide benefits. And also recently when I have started in India, so a lot of people are also starting to use TwoFlow. Like example is FMIC Bihar in Patna. So they have started to use TwoFlow, and NIH, as you know, Roorkee has been interested in using TwoFlow, and as well as CWC. So a lot of companies and people are trying to move to TwoFlow software. So I would just like to say what are the products which TwoFlow has. As I said, S-tree is the 1D component. So you see this is advanced pipe networks as well as 1D open channel flows. So all the 1D components of any of the software is called as S-tree in TwoFlow, and TwoFlow Classic is the fixed grid based approach. So it has a fixed grid approach, and it is mostly useful for flood modeling applications. And this is TwoFlow FE. FE stands for finite volume. it mostly FE, we use FE for the environmental applications because of the modules it supports, like advection dispersion, sediment transport, morphology, and water quality. So this is based on flexible mesh approach. So there are these three are the three products which Tuflo has. Basically, if Tuflo Classic, it has inbuilt S3 as well, so they are not separate. So it's all part of one component for flood modeling. And Tuflo is based on a different solver and a different schema. So the schema here is flexible mesh-based approach, and here it is a fixed grid approach. So these are some of the internal differences between them. And I would like to say, like, what makes Tuflo is special. Like, so we try to listen to the clients and try to uh, improve our modeling features based on the feedback. So that is one. And we are the developers and users of the software. So if you see Tuflo's, it has been extensively benchmarked for last 45 years. So there's some of the reports which are available in the website. So you can go through these reports for benchmarking studies for which was done using Tuflo. And it has been calibrated for thousands of real world studies. So one thing is benchmarking the software for any small case test case scenario, and the other thing is trying to calibrate the model with some real world event. So there are thousands of events which Tuflo was calibrated for. You can see these reports. It's mostly in the Australian context, which it was calibrated, which we have the reports, but it is not any different for any other country as well. So now when it comes to speed, this is one of the most important features of TwoFlow. Um, TwoFlow is the fastest 2D shallow water equation solver available currently in the market. So this is not just out of the air. There was one study done by the UK's Environmental Agency. This is a report which is available in the website too. So they have done, they have compared different hydraulic modeling solvers for the speed, accuracy, as well as model flexibility. So one specific test is the test 7, which is somewhat similar to a real world case. And now, so they compared different solvers for its speed. Now with TwoFlow Classic, with one CPU, it takes 3.3 minutes, whereas Mike Flood with even 8 CPUs, it takes 3.8 minutes, and Hecrus with 8 CPUs, it takes 34 minutes, which is way slower. And now, as an add-on, if we have a TwoFlow GPU module, it is 10 to 100 times faster than TwoFlow Classic. So overall, we can say that TwoFlow is way much faster than any other softwares, and that gives us like a lot of advantages when you're modeling large scale scenarios. So I'll show you some of the examples where TwoFlow's GPU module with its speed is being used widely. Now, when it comes to stability, everyone would like to have a stable model which gives a proper results. So the stability is always connected to the numerical accuracy. So how accurate are we able to model the real-time scenarios? So one thing is stability. It has an exceptional 1D, 2D stability. So this is a tsunami assessment which you can see on the screen. So if a model can predict such a high water level gradients across a domain, so that is a statement of a model being very stable. And it has most advanced 1D 2D linking schemes. So TwoFlow is the first software solver to incorporate the 1D 2D linking scheme back in 1980. So from then it has incorporated the most efficient 1D 2D linking schemes, and there are no wetting and drying issues at all in your model. Your cells can get wet or dry at any point of time, and it has an excellent error messaging capability. So when you're doing any modeling, if there's any error in your model, so it will show you an error code, which you can go back to the TwoFlow's website and see what is the possible resolution for that error and how to, what you'll have some knowledge about how the error would propagate or what happens with this error. So it has a lot of checks, errors, and warning messages, which it gives you. And as I said, TwoFlow team does a lot of these kind of tests. So this is a lab flume test for the tsunami inundation extent into the urban area. So this is an urban area, and we are trying to simulate the extent of tsunami propagation. So you can see this is the real-time case, and this is the model case. So the real-time case and model case matches really well. Now, when it comes to model build flexibility, TwoFlow is built for its flexibility and known for its flexibility, because you can, using any of these graphic GIS softwares, you can build your models so that So with this capability, everyone knows are aware of GIS softwares nowadays, so they can use the capabilities of that, as well as they can do a lot of automations and programming to help their model build. And if you don't like somebody don't use much of GIS, they can prefer graphic interface providers. So these are all the graphic interface providers who use ToFlow engine, basically numerical engine, and they build their product with the graphic interface. Apart from that, there are a variety of third-party apps. So one specific app, one plugin is called as ToFlow QGIS plugin. So QGIS is a free source software. Within this, there's a free source plugin called as ToFlow plugin. So you can use this to build your layers, view your layers, as well as analyze your modeling results. Animations and all can be done within ToFlow QGIS plugin. I'll show this plugin a bit of details of this shortly. Now, when it comes, we have an excellent support team. If you have any questions in your model build or how you want to represent a real-time case, or if you have any errors in your model with stability, we are always there to support you. And it is the cost is much is just a fraction of any other commercial software solvers, and it has less licensing limitations and complexities as well. So we won't be going much into that, but what I would like to show you is a bit of applications of an urban model. So if this is an urban 2D only model and there is an inflow at the top of the boundary and you route the flow through the domain, and basically you are comparing here with various locations within this model. So just play this result. So this is a flood model basically, and you're trying to calibrate the model with various recorded as well as model results. So the red line is the model result and the blue dots are the recorded levels. So you can see at all the locations ToFlow calibrates really well. And so this is since 1989, we have developed a 2D solver, and since then we are using the same solver for our applications. The next part is the 1D 2D floodplain modeling, which is why ToFlow is very popular even till today. The 1D 2D is most advanced scheme because ToFlow is the first software solver to incorporate the 1D 2D linking scheme. So if I just like to show you how the 1D 2D linking scheme works. So if this is a flood extent model, and if you want to zoom in into this area, so this is a zoomed in of that area. And you can see this is the river channel, and this is called as 1D component, and we are linking that with the 2D area. So this is all the floodplain is a 2D area. So we're trying to link the 1D to 2D, and this is pretty much an old animation, but you can really see how once it processes the flood banks of the 1D area, it goes into the 2D, and there's also within that same level, it comes back into the 1D if there's a water level downstream is higher, so it will come back into the 1D. So this 1D 2D linking scheme is most advanced, and so this is what really happens in a real-time case. So if there's a river flowing and if it exceeds the bank levels, so it goes into the 2D, and when it dries up into the river bank, it comes back into the river channel. So that interaction is well represented in the 1D 2D linking schemes. And as I think the most relevant aspect to this session is the integrated catchment modeling. So this has been incorporated into ToFlow in 2006, and since then it is being widely popular. So this is an urban area, and you can see the red lines are the underground stormwater network, and we are applying a rainfall total of 486 mm. So this is a rainfall, and we are applying an infiltration of 2 mm per hour as a constant infiltration for this model. So this is a direct rainfall model, and we are trying to model the integrated catchment. So this is a catchment area, and we are trying to integrate that with the stormwater network, and how is stormwater inundation within that would work. So that is the criteria. And now, so here this is a underground. I'm just zooming into one of the location here of pipe. So this is one pipe, and how the flows which inside the pipe would behave is what is the flows in the pipe, as well as this is a long section of the pipe. You can see there are 6 pipes. So these are the 6 pipes, and this is a long section plot of that. So you can see this is the maximum water level, the blue line, and this is the bed level, and this is the water level. How it varies dynamically within the pipe, and you can see the red dots are the pit levels. So pits means it will incorporate, it will take in the flows from the overground and transfer it to the pipe. And once the pipe gets filled up, it again surcharges and goes into the ground level. So this is the pit levels, what we call. So I'll explain you more of these in detail in the next presentation too. So just understand this is an integrated catchment model where we are modeling the underground stormwater network to the overland flow. So everything is linked up dynamically. It's not like separately we model the underground pipe network as 1D, and then we link up in specific areas. It's like integrated fully into the 1D, 2D model. So the next few things which I'll quickly go over is the rainfall model. It's a direct rainfall catchment modeling is what we call it. So if see, this is a very large area in one of the east coast of Australia. So it's around 600 kilometers by 600 kilometers square is the area of the catchment. And we are applying a direct rainfall. So this is the rainfall what we are applying. And you can see the flows through the catchment with the rainfall. So this is it has around 30 meters of grid, and this model was taking around 48 hours of simulation time. So such a huge extent of area. You can see it's around 36,000 kilometers square, and with 30 meters of resolution, it still runs in within 10 hours or 15 hours. So that is very much helpful in terms of flood forecasting, flood warning systems for such a big area. I'll show you one example here too. So this is one example for flood prediction and warning systems. So you can see the rainfall intensity as it deposits lots of water in the floodplain. So this is the green line. The green is the one which is the rainfall intensity, and this is the flood indication due to that. And now we can use this for flood warning systems. So one example which I can say which was used in USA with application of real-time flood predictions is that in USA they have the university which is called as the University of Virginia. So they have developed a flood model and hosted it in the cloud. So that flood model, what it does is that it will take the NOVA grids, the NOVA rainfall grids, and convert it into two-flow input format, and then simulate the model in the cloud. And those results it will transfer to the transport department based on certain criteria. So only the grids, if it is more than certain trigger level, so based on that, it will run the simulations and give the results. So that kind of automation is very much possible for real-time flood prediction systems. So a similar kind of case was done in Bagmati River in India as well with using two-flow software. So I'll tell you those examples in the next few sessions as well. So the next most important aspect also for urban stormwater network is the application of Quadtree. I think now this name has become quite popular nowadays. So Quadtree, as you see, what is the meaning of Quadtree is that it is a we can every single cell will have four cells within that. So quad, that is the meaning of quad. So if you see here, usually in the fixed grid approach, you can have only one single cell. But now with Quadtree, we can vary the cell size within a single model. So this cell's outside cell size might have 5 meters. Inside it can have it as 1 meter or 2 meters. So if this is the road network, we can have 1 meter of cell size within that area. And outside that area, we can have a coarser resolution. So now with this, it's very useful for stormwater or urban network modeling, where you can have a finer resolution within the drainage areas. And outside that, we can have a very coarse resolution, which we don't need that kind of accuracy. With this, we are not compromising on the speed, but still we are getting the best accuracy as possible. The next part also, which was the TwoFlow's recent release, was the subgrid sampling. I'll explain you not in this is not very much relevant to urban networks or urban water management, but it's very useful in terms of accuracy of the model. So if you see what is SGS stands for subgrid sampling. So here in TwoFlow's schematization, the cell center is this. So some solvers use only cell center only for their model discretization, but TwoFlow uses cell center as well as cell faces. So this is based on TwoFlow schema. Cell faces for the elevations basically. So these are the elevations and cell center elevation it will take. So this usually it is good if there's no variation within a single cell. But if so, this is the classic approach. So where we have so this is a river channel, and this is a floodplain, and so this is a single cell. So we can have a cell center and cell faces like this. So it's kind of flat bucket approach. So whatever is this cell will have a single elevation all across the cell based on the cell center. But now, if not, if you are applying a subgrid sampling, it will sample the points within the cell. So it will sample the points all along this and pick up this river channel as well as the floodplain like this. And now we are having a better representation of a cell. So earlier we had to reduce the cell size, or we had to do some approximation to incorporate this kind of variation. But now with subgrid sampling, with this same cell resolution, we're able to get a varying topographic features. So now with this, we're getting best accuracy as well. Basically, the best hydraulic conductivity. And TwoFlow is very much popular for it has all inbuilt features for flood early warning systems. So the root closures, and as well as it can predict what is the time it will take for the flood to reach a property. So these are the different times which are available to reach a property. And also TwoFlow is compatible with flood early warning systems like Delft, FEWS, and Flood Intel. So one feature which is also useful is the dam failure inundation. Uh, so I was also part of this big, huge project by the UK's environmental agency. So there were three big consultants who use the TwoFlow's HPC for dam failure inundation. It's very useful for dams because the TwoFlow HPC is based on adaptive time stepping. So it will change the time step based on the model stability. So that is very useful for dams when there's a huge flow of water. The stability of the model is very critical, and TwoFlow will adjust the time step based on the conditions there. So and also with TwoFlow GPU, so that is why instead of all the softwares, TwoFlow is specifically selected for modeling all the dams in UK for the dam bridge inundation studies. So this is some of the results for this is a lab flow experiment where there's a huge volume of water release and there's an obstruction. So this obstruction is intentionally kept oblique because to study the flow field around the obstruction, how it varies within that. So this is the obstruction flow field and how it goes. And so apart from that, I'll just like to show some of the applications where TwoFlow is useful for advection dispersion mechanism as well. So for the pollutant plume assessments, it can be used. So this is a pollutant which was dropped into the river channel and how it flows along the ground, along the river channel, it can be studied. So because of the component of advection dispersion. And apart from that, there's also, it can be used for residence time assessments. So this is somewhat opposite case where we are having a concentration of 100% throughout this model. Throughout the model, and we are trying to apply a tidal flows as well as the river flows, and how will that affect the concentrations within the lake? This is called as coastal lake. So how will it affect the concentrations within that, and how it can be useful for flushing studies? So we can how long it will take to flush out the contaminant or the concentration from the model is what we can study here. So this is based on TwoFlow Classic HPC or FE, which is based on advection dispersion schema. And also TwoFlow has a 3D module as well. So if you have a tracer here, so we can study the two-dimensional view as well as if you see that this is a three-dimensional view of it. So this is a two-dimensional, this is a three-dimensional part. So this is the profile, and you can see the concentrations within the area here along this black line here and this black line here. So this is a outfall study which is used. And TwoFlow also is useful for 3D water quality assessments. So when I say water quality, the most important for estuaries is the saltwater freshwater interaction. So the saltwater intrusion areas also we can study. So here, so this is for a so there's we are trying to study the saltwater intrusion or the interactions here. So this is the saltwater area, and this is the freshwater which is coming through the channel. So this is the location, and we are applying a tidal inflow boundary. So this is the saltwater concentration. You can see that 35 ppm is the saltwater, and this is the sea water area, and this is the freshwater. And how the based on the tides it varies, and you can see the concentrations vertically as well with the 3D water quality module. And we have just calibrated the model and data, the recorded levels, and it calibrates really well. As well as we can, within this, we also have a temperature module. So with that, we can simulate the incoming temperature as well as the seawater temperature and how it interacts with the salinity is what we can study. And this is the temperature with the depths also we can analyze. So there's a salinity module as well as the temperature within the advection dispersion scheme. So this is all part of advection dispersion. So basically what it does is when saltwater is kind of a contaminant with certain concentration of salinity, and how it propagates within, how it interacts with the freshwater, and density dependent flows is what we can simulate with the TwoFlow FE. So just make understand that this is TwoFlow part of TwoFlow FE. So TwoFlow FE is a fixed grid based approach. FE stands for finite volume, but it's kind of a flexible mesh approach. Also, to flow FE, there's also water quality module, which is based on the AED, which it is called as. So AED is the software solver for the water quality, which is developed by the University of Western Australia. So they have developed the software solver for the water quality. So these are the different parameters which it can simulate. And now Tuflo FE is now integrated with the AED software for modeling all the water quality parameters. So dissolved oxygen, nitrogen, phosphorus cycles, and you can do pathogens as well as phytoplanktons and zooplanktons. So a lot of almost all the water quality parameters can be simulated with the Tuflo FE. So basically, what it does is it will link the hydrodynamic module to the water quality module and how the hydrodynamics, basically the salinity, temperature, and uh, and the water levels and velocities, all the hydrodynamics as well as the water quality concentrations will affect the microorganisms. So all these water quality parameters can be simulated. So AED is a software solver developed by the University of Western Australia. So we have just linked up with them in implementing in connecting our software solver to the AED system. And TUFLOW FE is also has a water as a module for sediment transport. So sediment transport is very much popular for river morphology as well as coastal or port studies, where we need to study the effect of dredging. So this is the study for an effect of dredging. So to study the effect of dredging, we are just so this is a natural sediment. So you can see the sediment transport when in a natural profile of river flows, and this is the total sediment due to dredging. You can see due to dredging, the sediment like suspended solid stress sediment will increase. So this is for total sediment and this is for natural sediment. And if you want to understand what is the dredging part of the sediment, we can, if we subtract post-process total sediment with the natural sediment, you'll get what is the dredging sediment. So that is what we are trying to understand in this study. So what is the dredging part of sedimentation which will occur? And now we can see what is the ADCP recording and modeled area. So this is just for validation purposes. So we have a 3D module with this is a port channel, and this is the ADCP recording of the sediments within the port channel, and this is the modeled results. So it matches quite accurate, quite well. So that is where it is more widely used. And the last part is TUFL also has a cyclone, hurricane, typhoon, storm, tide modeling areas, because basically for all of these, the another additional parameter which it requires is inclusion of a wave wind field as well as pressure field. So a cyclone is nothing but a combination of pressure as well as wind field over the large coastal area, and as well as it has temperature as well as other factors uh, which will affect the cyclone moment. So those predictions can be done with 2FE. So the cyclone moment as well as hurricane, typhoon, stormwater modeling can be done. So for storm tide modeling, once we can predict what is the water levels which will come at the coast, and from that we can understand what would this storm levels or the tide levels due to the storm will affect the coastal urban areas, or whatever is the coastal towns. How will it affect the tides? Will affect the coastal areas. We can study with stormwater modeling. I mean storm tide modeling, that is called as. So this is all what Tuflo is widely used for. And this is just a presentation or brief overview of the TUFLOW software. What are the applications and what are the benefits of TUFLOW and where it is used. So all this we have just combined and just given you kind of an overview of the software. Now next we'll go specifically to the topic of this session which you're going through. So that is for urban stormwater network. So I'll just go through some of the theory for urban stormwater network. Then we'll have some tools which are built into TUFLOW for urban stormwater network. And after that, I'll show you, I think, two examples if we have time. One is an example of stormwater network in London, as well as I'll show you another example which for a stormwater network in Delhi city. So I have built the stormwater network for Delhi city, for the Delhi metropolitan area, with having all the pipe networks as well as rainfall data. So I'll just show you that aspect as well, how it is being implemented into Flow. So I'll share you that presentation, the next presentation. If you have any questions, you can ask me now. I'll go to the next presentation. Okay, yeah. So you're able to see my screen? Okay. Okay, yeah. You can see my screen now. Yeah. Oh, just a minute.
About swim model, EPA swim. There is
Yes.
one
Okay.
commercially available software that is called PC swim, but they
Okay.
are
Yes.
very much, they are happy to provide that software PC swim, which has a little bit more capabilities, and basically the front end is different, and also you can get more data outputs in different form. And they are very much happy to provide that software to university students, those who are in research. So if you write to them and say, look, we need this software for a few years for our research purposes, I think they will be very happy to provide that. But you have to contact them directly. But it has a little bit more capability than EPSU. They're using the same engine, but they have changed the presentation, the input data and output data for me.
So, but I think this TCSW,
PC swim, yeah.
TCSW, I don't know whether they directly provide it from Canada, because in India they have an office in Bangalore. And what I understand, my student had used it. So he had provided it for a year.
So,
but they are very fussy about providing even that. And that is my experience.
okay.
But of course, my student got it for 1 year.
They can extend it for another year.
That was very difficult. In fact,
Okay.
we had to suddenly close down the work because they said that they will not extend.
Okay.
But later we procured it.
Yeah.
I think 10 licenses cost something like 5 lakhs or something.
Yeah, it is expensive. And that's why it is good to use EPS swim.
But EPS swim actually using is also not that easy, and because it's interface in the
Interface is a little bit difficult. Yeah, that's why they're charging such a huge amount of money.
No, but 5 lakhs cost 10 licenses, not too high.
No, not too bad. Yeah. But they're normally very happy to extend. But in your case, they were not that forthcoming. But I got
They have an office in Bangalore.
Bangalore, yeah.
Not exactly one person that we had is single man.
Yeah. No, but my experience is that they easily extended for 3 years for one of my PhD students.
In India, I find that I have found support from Mike is
much better. Okay.
They provide to students, especially if you have some needs.
Right. Okay.
Mike is quite popular.
Mike is also very popular.
So I think, sir, you're talking about the EPS swim, right? SWMM swim software.
Yeah. So what we are
Okay.
interested to know that this Q-flow, whether it is available for academic purposes at a reduced cost or even available for a small period of time, a year or two, without any charges.
Yes, yeah. So so in Tuflo there are two things. One thing is for education institutions there's 50% discount from whatever is the list price. So there's 50% discount. And apart from that, if you want to, you have a trial of Tuflo. I mean, there's a demo mode where within certain pipe networks, say around I think 200 pipe networks, we can model it without any license. So that is called as demo mode. And apart from that, if you want a full version trial license for, I think they give for 1 month or 2 months as a full trial license also, it is possible to be given. So these are different ways. And as well as, I'm happy to give training sessions as well. I think last month itself, I've given a training session at WRDM department. So I'm happy giving training sessions as well. So yeah, so that is all. And I think EP Swim, I was thinking it was a free source software. So as you say, it is not free source, EP Swim, SWMM Swim.
Yeah.
So okay. So because I'll show you in the next presentation, I think. So the EP Swim network for the Delhi model network. So for all of the Delhi's like we have a master plan for Delhi city. So IIT Delhi is doing that master plan with the EPS Swim. So they had done previously, and now since they have brought the software, they want to convert all their EP Swim models to 2Flow. So what I found that EP Swim doesn't have a 2D model. Means it doesn't have how it the flood inundation we cannot see. We can just model the 1D networks. I mean, we can model the pipe network, but we can't do how it will translate to the urban flood areas. So I'll show you that example. I have it with me now. So I have a swim model, and they just given me the swim model, and I converted that to 2Flow, and I'm studying the I mean, the flood inundation due to that area. I mean, in that area. So I'll show you that in next presentation, so that you'll get more understanding of that. I'll show you. Yes. I'll show you then we can talk more on it. So I think I'll just share my screen and I'll show you that. Yeah. So this is a bit of basics about stormwater. I mean, for the stormwater modeling, but it will also cover some of the tools which 2Flow has. So in few of these cases, I'll be focusing on a manual called as QUDM. So QUDM is the urban stormwater, and it's called as Queensland Urban Drainage Model. So Queensland is a state in Australia. So they, for each state, will have their own manual for stormwater networks. So I'll show you, this is one of the pipe areas, and you can see this is the floor level and this is the house. So this is a road network and this is the underground pipe network. So whatever rain falls on the road, we are not trying to, we're just trying to cutter it within the road area and taking it into the underground network, rather than letting it flow into the outside area and go into the houses. So will just go over the pipe networks theory for now, like what are the losses and how does the pipe network behave in any model basically. And what are some of the quality checks in 2Flow plugin, which 2Flow has. So we'll see some of the quality checks, and we'll see some of the like real-time projects, as I said, for two stormwater networks. One is for London City we have, as well as for New Delhi. I've just done it last week. So I'll just show you those examples as well. So I'll show you some of the theory. So what basically, which we will cover in theory, is the pipe flow regimes. So an energy losses with friction, junctions, and manholes, and overland flow captures, surcharging, blockages, and operational structures. So here, what we'll be doing is pipe flow regimes. You can see every pipe will have a flow regime, like an inlet control flow, outlet control flow, and is it critical flow, subcritical flows, and supercritical flow, and is it drowned out, and how are the conditions at the entrance and the exit. So these are the flow regimes which will matter based on the flow in the pipe. And the most important aspect is the energy losses. So there was a lot of studies done in majority of Indian areas, like there was Bangalore, Delhi, and other places where the major factor for flooding, for urban flooding, is due to the losses due to junctions and manholes. So due to improper design of manholes, junctions, there's a lot of loss, which because of that, the pipe is not going at full capacity. So due to that, there's a surcharge in the pipe networks and there will be overflow from the pipe. And there's also called as overland flow captures. So these are the pits which will capture the overland flows, surcharging blockages. And operational structures are a different kind of thing where there's some kind of pumping or is any operational with the structures like VS and all will be varied based on the conditions of flow. So that is called as operational structures. So we'll just touch upon all these things very briefly. So very quickly, I can show you some of the terminologies. So as you know, the HGL, the hydraulic grade line, it is basically essentially the water level within the pipe. So if it is a half full, like partially full pipe, the HGL is the water level. And if it is beyond the pipe, the pipe size, then if you have any kind of a pipe and whatever is the height which it would come, so that will be the HGL of the flowing pipe, and the total energy is the whatever is the HGL plus the V square by 2G. This is the total the velocity head. So V square by 2G is the kinetic energy of the flow, and H is the like whatever is the hydraulic fluid line for that. So this is basic theory about the pipe flows. And basically here we are talking about pipe energies because we want to understand how is the energy loss coefficient K, which is incorporated into the velocity kinetic head. So whatever is energy loss is the K factor times V square by 2G is the energy loss coefficient. Now, I think you might already know about what is outlet pipe control. So outlet control flow occurs where the downstream water level influences the flow rate. So outlet control means the outlet of the pipe is controlling the flow within the pipe. So the conditions for that, if the flow is subcritical or pressurized, so this is when the inlet and outlet energy and friction losses apply. If not, if it is a free flow or if it is a critical flow, then the only energy which loss which will apply is the inlet energy as well as friction losses. So if it's an outlet control, all the three losses, inlet, outlet, as well as friction losses will apply. If it is a free flow, only inlet and friction losses will apply. So if it is a critical flow, you can see this DC is the critical flow at the outlet. So this is when inlet and friction losses only will apply. So this all diagrams are from the QUTM manual. So this is Queensland Urban Drainage Manual 2016. So now we'll look at what is the inlet control flows. So this is most common one, I think, because if the flow is supercritical or if it's a very steep channel, so that is when it is under inlet control conditions. So if it's supercritical, sufficiently steep, and if it is having an orifice flow, so orifice flow will also transfer into having an inlet control flow. So this is one note. And so basically a few equations I'll tell, like, as you know, the friction energy loss is we'll be using HF, which is this, and we'll be trying to calculate what is the friction SF loss with the L is length of the pipe and SF is a factor. So we'll be using these equations for calculating the friction loss. So if it is from fully flowing pipe, then it's easier to calculate because R is the hydraulic radius is smaller by 2. But if it is a partially full flowing pipe, then it will be shifted to kind of indeterminate equations, which is not very straightforward. So there's some guidance in literatures available generally for friction or the Manning's roughness within the pipe network. So this is the most common recommendations for the Manning's roughness with pipes. If you're trying to go outside these recommendations, you need to really justify why we are trying to go outside the recommended values. So, and this is a kind of CFD model to understand what is the flow within the pipe. So you can see how the pipe junctions, if it is aligned in that way, how the flow will vary with I mean, these are the kind of streamlines. So if there's junctions like this, how the flow, how different or how smooth the flow field is. So this is what will define the K parameter. So if there's a high, like huge loss, the K will be high. If there's a lesser loss, we'll be having a lesser K value. So that is the energy loss at the manholes, junctions, bends, and if there's any obstructions. So basically, I would say like what is the requirements or the need for having manholes. So manhole, one factor is to access for construction and maintenance purposes. The other thing is for accommodating the pipe transitions and changes. So if there's any two connecting pipe networks or any transition changes from different sizes, say from a 2 meters pipe to a 10 meters pipe, you are transitioning that. So we'll have to have a manhole to transition that, and also to receive the flow from the overground inlets. So this is the inlet from the overground. So we need to receive the flow and transfer it to the pipe network. So that is where we'll be using the manholes. Now I'll just give a brief about what causes the manhole losses. So if this is the incoming, this is one pipe, and this is the downstream pipe, and this is a manhole. So the majority of the losses due to manhole is due to expansion of flows. So water always like to flow from its initial position. It doesn't like to expand or contract. Once it is trying to expand, that is when the losses would occur. So this is the losses due to expansion at inlets. And at the downstream also there's a contraction. So that is when there's a loss here. And there's also vena contracta, which forms under the pipe here. So, and also there's additional turbulence within the chamber due to other factors, which is, I'll tell you next slide. as to why the turbulence would happen. So the other turbulence which will occur for the pipe networks is the difference in alignment. You can see this is a different alignment from this pipe. So if the two pipes are in different alignment, so we'll get an additional losses due to the bends which will occur to the streamlines. So that is one, and also change in vertical alignment. You can see this is in different aligned to this pipe, which is a differently aligned network. So we'll get bigger losses here, and essentially will not be, once we get bigger losses, will not be essentially utilizing this full flow capacity of the pipe. Once we're not having the full flow capacity of this pipe, it will surcharge into the overground here and it will flood the area. Even though we are having a bigger pipe network, it will not be useful at all for our purpose. So these are some of the losses in the pipe manhole inlet and outlet losses. So in most cases, most software also uses a fixed K values. So this is some of the recommendations for the value of K based on the D by D and extension losses and everything. So these are some of them in our urban drainage manuals, it will be given. So, but it's most useful to understand, we need to vary K with the flow conditions. So we can't have a constant K value for the flow at low flows as well as high flows. So based on the conditions, we need to vary the flow. So to flow, currently it has a dynamic varying K value based on different loss components. So it will recalculate the K at every time step. So it will recalculate the loss at every time step to suit the dynamic flow conditions. So if so it basically it uses a summation of different K values. I mean different inlet loss, outlet loss. This kind of summation of different loss factors. So again, this function is dependent on the QI, which for each pipe, what is the fraction of flow within that pipe and summation of flows in all the pipes. So that is what the K, which is a loss, finally will depend on. And also if it has change in pipe invert levels, so that is also which has a different equation for K with different elevations. Z stands for elevation. So, like our major factor when you're designing any urban stormwater network is to reduce the losses or whatever is the loss with the manhole. We cannot go without a manhole, definitely. So we have to have a manhole, but we have to reduce the losses within a manhole. So one thing is to keep the chamber size to the minimum. So we can keep the chamber size to minimum so that the losses are minimized. And we need to minimize the turbulence or the eddies which forms in the manhole as well as through the outlet. And benching is one, and we need to minimize the minor contractor based on the shape of the pipes at the corners. So if you try to round off the corners, the minor contractor effect will be reducing. So that is one. So you can see the shape here. So the minor contractor forms at the construction area. So here when it forms here, so we need to reduce the minor contractor mechanism to reduce the losses basically. So yeah, so this is where we are trying to minimize maximum winner contractor width to reduce the winner contractor velocity. So this is the ones. And the other important feature for any urban drainage network is the inlets. So inlets, when I say it's quite interchangeably used, you can use it as inlets, pipes, pits, drains, or gully traps. So all of the functions are the same. There might be a bit of differences in this discharge capacities as well as the type of the structure, but the function of it is the same to transfer the water to the underground pipe network. So so there are many approaches how we model these inlets into any software. And also we need to understand it can also backflow into the overground. So if the underground pipe network is full, so it will flow back into the overland flow, and that is called as surcharging. So that also we need to have that model capability to backflow surcharge into the model. There are different terminologies, but as I said, it's the same function. Pits, inlets, curbs. So inlets and curb inlets are more known for the road network, for the road drainage design. And drains, gully traps, these are all part of the same functionality. The next, as I said, the most important factor for any pit is to convey the flow as per whatever it is supposed to do. But in few cases, it doesn't have that because when the flow rate is high over the ground, the flow within this will be reduced definitely. So that we need to see what is the real-time flow inlet capacity and what is the flow capacity of that within the ideal conditions. So we need to see what is that and try to represent that in the model. What is the flow capacity? So basically, we give this kind of depth flow curves for each inlet. We have a curve for depth versus flow. So if this is the depth of water, what is the flow it can take into the pipes? So this is the depth flow curves, which is most popular in using. So these curves will be given by the manufacturer. So if there's a manufacturer for the pits, so they give us based on their experiments as well as observation values. They give us what is the depth versus flow curve. So this is the depth versus flow curve at different places, and that is what they give. And so we'll be able to model the if it is in ponded water, we need to be best possible. We try to model those areas as well as there's high probability of debris impeding the flow. So if there's any debris, you can see say some parts of debris. So that is the most important factor in our Indian case as well. So if there's any blockages and all, so that will not have the full functionality of the inlet to convey the water. So that is when we need to have a proper mechanism or maintenance thing to remove the debris and then do the proper checks so that the pits are fully functional. And also this is kind of backflow which it will occur. So if there's any flooding which occurs downstream and it is not able to basically discharge the water, so that is when there's a backflow in the pipe and all the manholes will just be blown out of that area. Or I'll show you that in the next slide. Or this is where the backflows which will be done. So one of the causes for backflows is pipe design capacity. So obviously, when your pipe design capacity is exceeding, it will put pressure on the manholes because the pressure of the horizontal flow is less than the vertical pressure. So that will lead to blowing of the manholes. And and also there's a blockage in the pipe network. So if there's any blockage in the pipes itself, it will have a backflow. Also, when there's a receiving waters, so if there's any high tide levels, or any river flood which is occurring at the downstream, so that will cause the water to backflow. So we need to have a proper maintenance as well as modeling considerations to prevent these backflows. So I'll show you the next slide too. So this is what backflows when I say backflow from the pipe network. So it will just blow off these manholes due to the pressure in the networks. So this is also for another manhole. So when we're doing modeling, it is very important to have a factor for these conditions and see when this lid will pop up as well. So in most drainage manuals, so this is again, as I said, QUDM, Queensland Urban Drainage Manual. So they specify what is the design value and severe conditions, what is the blockage factors. So when we're doing modeling, we take this percentage factors and so if there's a 20% of blockage, what would be the flood mechanism? And if it's severe conditions, if it's 100% blockage, what would be the flood recommendations? So they have given guidance for various inlet types. So this is again, we need a major problem for trash racks and gross pollutant traps. Debris deflectors can be given to reduce this problem, and there's maintenance programs. So this is all how we manage the blockage scenarios. And I think that's all for the theory part. So I'll just go to the next part for doing the quality checks uh, in the TwoFlow software. So I'll just give a brief of that too. So we'll just go for a break and come back for 10 minutes. If you have any questions, if you want to discuss. So the next session will be mostly on focusing on the software and practical aspect of the model build. So we'll see how we have different aspects of software. You have any questions, you can ask me.
Rishi, can we have a break for 10 minutes?
Yes, yeah, we'll have a break for 10 minutes. We'll have to break for 10 minutes and come back at, I think 10:50 will be fine. 11:50, sorry.
One thing more before you go, Rishi. This Queensland
Yes.
manual, urban drainage manual. Is it available in
Yes.
public domain? So that,
Yeah, it is available in public domain. I have downloaded that as well. I can share. It's very good manual for even our any context
yes,
because it's very well.
that's why I'm interested that we can circulate it among our
Oh,
participants over here so that they can use it.
yes,
Uh,
yes, yeah. Mhm. Yeah, I will forward that. I'll send you to Professor P.K. Shamasar and then you can forward to all the participants. Yes, yes, yeah. Actually, this QEDM manual, it's not only for Australia, even though it was developed for Australia, it is quite popular in terms of the technical things which are there in that. It's very good for understanding the urban drainage aspects. So it's very useful for all other people as well.
I know I've seen it and I've used it in my when I was working in Queensland. There's a very good manual providing.
Yes. Yes, sir. Yeah, it's very good. Yes.
Actually, see,
Okay. Yes, sir. Yes, sir. Yeah. Okay. Okay. So thank you very much. Yes, sir. So at 11:50 like that will be. Okay. Okay. Yeah. 11:50.
you can have a cup of tea.
Please stop taking.